And then, do you guys know if everyone was present for the other group?
I didn't see any of them.
The lab people?
Mm-hmm.
I saw Cattell, I think I went and looked.
Okay.
I think they're all there.
Okay. I can double check when everyone makes it up here for review, but okay. And then let's share this. Okay, so we're reviewing for our exam in components class. And let me put the review sheet up on the screen. Okay. Okay. So, short list of definitions, right? Be able to talk about net positive suction head available and cavitation.
What is net positive suction head available?
So let's pull up the DOE handbook definition. So you have the specific definition, and then we'll talk about what it is. So let me open the DOE handbook. I think it's volume 1, and I think it's module 3, if I remember correctly. I am correct. Okay, so under centrifugal pump operation, on page 12, there is the definition, which is the quantity used to determine if the pressure of the liquid being pumped is adequate to avoid cavitation is net positive suction head. The net positive suction head available is the difference between the pressure at the suction of the pump and the saturation pressure of the liquid being pumped. And net positive suction head required is the minimum net positive suction head necessary to avoid cavitation. So what they're saying is we've got cavitation, right? Which is when we have essentially low pressure that allows void bubbles to form in our fluid. And then when those collapse, that explosion in the fluid causes cavitation in our pump, right? And damage our pump. So in order to avoid that pressure creating that level of vacuum, you're going to have your net positive suction head required, right? So that's going to be how much suction you have to put through the pump to ensure that that low pressure doesn't form on the entrance to it, right? So available is how much of that you can take, and then the difference between those is your net positive suction head, how much you're actually doing, right? So required, available, and what you actually have.
Okay.
So it's essentially the pressure of the liquid being pumped through the actual pump. Make sense?
Yeah.
Okay. Then cavitation, we just kind of defined that as part of that first explanation. Head and head loss, and very specifically thinking about our first lab and how changing pipe size and length and fixtures affects head, which then affects flow rate. And just some of those relationships that we illustrated by actually having you measure things pump through different pipes, right? I'm not going to ask you to repeat the calculation from the lab, but I am going to ask you to be able to put it into your own words, what you observed happening, right? So we observed it, we did it mathematically. Now on the test, explain to me what you learned from that, okay? Gas binding in pumps, which that definition is in that same section after cavitation and pump curves. So this is essentially when you have too much gas or vapor mixed in, not in little collapsing bubbles, but just in the space, and now your impeller can't turn, okay? Shut off head, pump run out, which again, those are definitions right from the reading. And then turbulent and laminar flow, which we talked about in our first set of lectures and is in that little fluid dynamics overview reading that we had. Know the Reynolds number, where these transition and what they kind of look like and what causes it, right? Because we essentially have friction in our pipe, and as the water on the outside of our column of flow interacts with that pipe, it's going to have different speeds in the middle versus the outer edge of our cylinder of water that goes through that pipe, right? And then what a pump curve is, the typical shape for a centrifugal pump, and what that means. Like, you guys actually measured and created one, so you should be able to explain what information you can get from them, because you had to collect that information to make one, right? For number 2, expect a question along the lines of, explain what cavitation is and what it does to a pump, how you prevent it, and indications you as an operator would look for to know if it's happening. Okay, so what it is and what it does, and then the actual practical part is what is an operator going to look for or notice or be responsible for monitoring in order to notice it, and then common ways that we prevent it. I think there's a list of 5 in the DOE handbook. Probably have ready 2 or 3 of them that you just know this is what we do. So here with these definitions, kind of 3 and 4 are together, right? You should know what each of these are and what they do. And if I gave you a picture like this, you should be able to label the parts, right? And so I might ask you to label them and then explain what is the purpose of B, E, and H. That would be a question that you should expect to see. So then that fluid flow, we kind of already covered this one, right? Understand pipe sizing, sizing changes, what happens at bends, and especially be able to connect this to the concerns like water hammer, pipe burst and collapse, erosion, corrosion at pipe bends where there's high flow, the stuff we covered in that lecture in the videos associated with these issues. And then really, like I said, they're going to be primarily open-ended questions. Be able to explain how all these components we're learning about, what you interact with, right? We covered at length in our last lecture that while you may not be the pump maintenance technician, you need to know that there are particular ways that they do that maintenance so you can ensure the shaft isn't damaged and that bearings are replaced, and that as they're doing this maintenance, they're verifying that lubrication is hitting the gaskets and they're not dry and cracking, right? Those things you'd be looking for, even though you're not likely to be performing the maintenance, right? Connor will be now, but you guys need to be aware of those maintenance concerns and understand the big picture of this pump that's part of the system you're operating. So, pretty straightforward, easier exam in this class because we have so much lab work. That's the primary basis of your grade. Any questions?
Talk about pipe collapse for a minute, just real fast. I forget how it happens.
Essentially, if the pressure and suction through the pipe is becoming significantly enough negative, it pulls the pipe in on itself. And so that was the picture we showed of the pipe that had like the big dent in it. And so for whatever reason, the supply water is not matching the pressure you're sucking the water out with. And so it instead sucks the pipe in on itself.
So the suction out is high, it's going to pull the pipe in.
And also your influx is low. Both are occurring. But yeah. Yeah, Sam.
Water hammers like you shut off the valve really quick.
Right. So you got your velocity going forward, then all of a sudden you shut this really fast and it hits the solid wall and it bounces back. And all that energy translates back into the pipe. And you get vibration and potential valve and pipe damage. And the same thing can happen with steam hammer. Okay, it really is that straightforward and simple. So I'm going to end the Zoom meeting.